So in this video I'm going to talk about volumes of revolution. This is going to be a way of finding the volume of a solid that's formed by rotating it around either one of the axes or maybe a line. So for example, suppose I have this curve f of x and I want to find the volume of the solid formed by rotating this region, the region under the curve, around the x-axis. So you can visualize this wedge sort of rotating around the x-axis and tracing out this solid volume in which I have a circle that's traced out by the tip of this function all the way in a circle. It ends up looking sort of like a trumpet, right? This is, or a cone, that this is the base of the cone and this is the tip of the cone. And I want to find the volume of this solid. Our method for finding volumes is going to be really similar to what we did in previous videos, that I'm going to take this volume and I'm going to slice it up into a bunch of slices and find the volume of each of those slices. Let's pull out one slice, for example. So here's my slice. It sort of goes like this, and it is going to look like a really, almost, it's circular, but it's going to be a really flat cylinder. So my goal first is to find the volume of one slice. So let's consider this slice right here. So I've just sliced it. It looks something like this. Really, it looks like a coin. Because we have this circular face and we also have some width right here. And the face of the coin is a circle. And so that means that the surface area of the face of the slice is going to be the area of a circle, and the area of a circle is pi r squared. But in order to find volume, it's not just the area of the surface, we also need to know the width of each of these slices. And in this case, we're cutting up this region, this volume, along the x-axis. So each of these slices are going to be of width dx. And maybe I should call it delta x in this case because we haven't taken our limit yet. That this is the change in x value. And as our slices get closer and closer and closer together, it's going to be a more accurate representation of the volume. So the surface area of the face is the area of a circle, and then maybe I should call it the width is delta x. So my approximation of the volume, of the total volume, is going to be the sum of all of these slices. The sum as I goes from 1 to n of the area of each slice, and maybe I should just notate that I minus 1, times the width of each slice. And as I take the limit of these sums, we see that the volume is going to be given by the integral from the very first slice, which we're saying our slices start at a, to the very last slice, the slices end at a value of b. And notice that this measurement a to b is measuring along the x-axis because I'm measuring how many slices of bread I have. My bread goes from a to b as I slice up this cylinder. So that's my number of slices, and the volume of each slice is given by pi r squared times the width dx. This limit, the delta x, becomes this differential. And in my head, I'm thinking of this as the width of each slice, and this is the area of each piece of bread. And my A to B is telling me where the bread is. I'm not quite done though. because look at what we have in this formula. I'm integrating with respect to the variable x, but this formula has an r in it. And an r doesn't really make sense in this situation because I'm dealing with x's and y's. So in order to rewrite this, instead of using an r, we have to go back to the picture and see what is the radius. If I look at this example coin, the radius is this measure right here. And looking on this picture on the graph, we see the radius of each circle is changing. The radius depends upon which x value we're using as the base. And in this case, the height at each given x value is given exactly by this function. That's what a function does, that with an input of x, my output up here is the height along this function. So that's telling me that in this case, my f of x function is exactly the radius of each of these coin-shaped cylindrical regions. So that means my final formula for the volume is the integral from a to b of pi, instead of r, I'm going to put in my function f of x squared dx. And in my head, I can diagnose what each of these pieces are. This is where the region starts and where the region stops. I'm integrating with respect to x because that's how I'm taking each of the slices. The slices are split up in little x-sized pieces. And then the area of a circle is pi r squared. And in this case, the radius is given by the height of the function. Let's go ahead and work through an example of this using the formula. So suppose we want to rotate about the x-axis the solid enclosed by this curve y equals the square root of 4 minus x in the first quadrant. So I'm taking this piece. This is my function. F of x is y equals the square root of 4 minus x. And I want to rotate it about the x-axis. So the first thing that I want to do is draw the picture and try to be accurate about how I'm drawing the picture. Let's find the intercepts of this function. It's written to scale, but we can see that when x equals 0, y equals the square root of 4, which is 2. And when y equals 0, that's when we get the square root of 4 minus something equaling 0. That means that the x-intercept is 4. And I'll label this as x and y. When I rotate this around the x-axis, I get sort of a half egg shaped looking thing. Right? And I can visualize how I'm going to slice up this egg. I'm going to slice it up into a bunch of these coin-shaped bread sections, and each of the slices is going to have a width of dx, or delta x, because the slices are taking place along the x-axis. That's going to be important when we start rotating this around different curves. So let's set up our integration. So in this case, my integral is going to go from where my figure starts to where my figure stops in terms of x. Notice that I'm not going from -2 to 2 because that's not how I'm stacking my coins. I want to make sure that my bounds from a to b are where my coins start and where the coins stop, not the height of the coin. So it starts at x equals 0 and ends at x equals 4. And the area of the base of each of these slices, for one slice, it's going to be pi r squared, and the radius is given by the height of the function. So in this case, it's the square root of 4 minus x, all squared, pi r squared, and the width, when we take the limit, is this differential dx. So this is really the hard part. The hard part is setting up the integral, and now we can use the techniques of integration that we already know to be able to compute this. Thankfully, this is a nice function that the square root and the squared cancel, and so I'm left with the integral from 0 to 4, and I'm going to, because pi is just a constant, I can move that out front of the integral. I like it notationally. I think it makes it look a little cleaner. 4 minus x dx. Let's go ahead and integrate. The integral of 4 is 4x. The integral of x is 1/2 x squared. I'm raising the power, multiplying by the reciprocal, and I'm evaluating that as x goes from 0 to 4. That's pi 4 times 4 minus 1/2 of 4 squared is 16, which ends up being 4 times 4 is 16, and half of 16 is 8, so that ends up being 8 pi. Let's see another example, and this time instead of rotating it about the x-axis, we're going to rotate it about the y-axis, and we have to be a little bit careful about how we deal with rotations about the y-axis. So we're going to use the same region that we saw before, but we want to find the volume of the solid enclosed by y equals the square root of 4 minus x in the first quadrant. So we're starting with this as our region, but now we're going to rotate it about the y-axis. Notice that this gives us a different shape, and you wouldn't necessarily expect that this new shape would have the exact same volume. It still sort of looks like a half egg, but it's more of a dome shape, sort of the top half of the egg. Right, so that's what my new region looks like. And we're going to use the same method of slicing this up into a bunch of coins, but the coin slices are different. In our previous example, I'll put in a picture, we were slicing these coins vertically, and so each width was a dx width. In this case, now when we're breaking this up into these coin slices, the width is a dy width. It's a vertical width. So here's my example coin. And notice that the height of the coin in this case is a delta y. So when I integrate this, it's still going to be integrating using the formula pi r squared, but instead of a delta x, we're using a delta y. So for my integration, it has to be dy. What are the bounds of integration? The bounds of integration are going to be from where my coins start to where my coins stop. Labeling each of these pieces. The stack of coins starts where y is equal to 0. I'm integrating with respect to y, so I need to know the bounds in terms of y. They start where y equals 0 and end, the stack of coins ends at y equals 2. So this is my idea of an integral. I still haven't finished it because I have this r here and I need to convert r into a function of y. Let's look at what each of the radii of a given coin is going to be. So in contrast to what we saw before, where the radius was given by the height of the function, now the radius is this width here. Right? The radius of this coin is actually the x value. And so I need to relate this x value with whatever y value I'm putting in as an input. And the way to do that is with this function. So maybe my scratch work, we know that y is equal to the square root of 4 minus x. But this function is not the right function because I can't just plug in what the radius is. The radius is an x value. I don't have that written as in terms of y, so I need to solve and rewrite this as y squared equals 4 minus x. And solving for x, I get x equals 4 minus y squared. So instead of having this function, this is the function f of x, I now have a new function. This is g of y, a function that is the same function but just rewritten as a function of y. So that means that my integral in this case is going to be, as y goes from 0 to 2, of pi times the radius squared, and the radius is given by the inverse of this function, which is written as 4 minus y squared dy. The width of each coin is this little delta y width, and the radius of each coin is x, but we rewrote x in terms of y by solving for this function. That's the hard part. Now the easy part is to complete the integration. I'm going to pull the pi out front. I'm going to integrate from 0 to 2. I'm going to square this in my head. And don't forget the middle terms. That becomes 4 squared is 16. And then my middle terms are going to be minus 4y squared minus another 4y squared becomes minus 8y squared. You can write that out if you like. And then negative y squared squared is plus y to the 4th dy. Let's go ahead and integrate. The pi stays out front. I end up with 16y minus 8/3 y cubed plus 1/5, y to the 5th. I'm raising the power and multiplying by the reciprocal. And I'm going to evaluate that from y equals 0 to y equals 2. Notice that plugging in the lower bound just yields zeros. When I plug in the upper bound, I get pi 16 times 2 is 32, minus 2 to the 3rd is 8 times 8 is 64 thirds. 2 to the 5th is 32 plus 32 fifths. And this addition of fractions is something I don't want to do in my head. So I'm going to do it, on my calculator. 32 minus 64 thirds plus 32 fifths ends up being 17.06 repeating times pi. So notice that these two volumes were different when I rotated them around different axes, and it makes sense that this would be a little bigger because it's the wider football version.